Hello, good afternoon. It's already 3:30 and you can make a start on today's lecture CLO 5 on column. So as of this time, we have 23 participants. We are still waiting for 50 more. Yeah, we'll wait for 15 seconds. I've already shared the screen, on the screen, the slides for today's topic. And I also have uploaded today's materials in CN. So I hope you have downloaded it and have at your convenient location so that you can jot down any additional item that I might put in. Number two, I also have uploaded exercise sheets for column and strat. So those exercises meant for you to familiarize with the subject and to sharpen up your skill in problem solving. Okay. The third one, you have 3 more days before the attendance counting to make sure, well, they call it auto barring. Okay. If you have any issues on attendance, I think I have sorted out about 4 students. Those are late registrants or late registering students. Sort out their attendance. So if you still have that problem, just respond to me on either this MS Team or the best thing on email. And every time you communicate, make sure you put in your ID number. Now, because putting your name only is not sufficient to identify who you are. So make sure you put in your ID number. So today the participant now is 47, so it's only 50%. Okay. Okay, those are a few things there. So we'll start on today's lecture. We have done the case number 1 column, which is pin support at both ends of the column. The only difference between one end of the pin support is that it doesn't allow translation in Z, whereas on the other pin support it allows some translation in Z. That's the only minor difference. The rest on the pin support is that it allows rotation, so there is no bending moment, internal bending moment at the support. It doesn't allow any translation in X, Y, and at both supports. And we determine the critical load for that situation. We already got the critical load value, and also one example on how it is being calculated, and also the stress associated with that critical load, the compressive stress. And we apply it to one of the beam as an example there, and applying the fail-safe design philosophy. So that's for case 1. Now for today, we will look at case number 2 in detail. This is the second case where we solve the problem, solve the differential equations derived from it explicitly, and then to see that. So the other cases, the other 2 types of cases will be derived, will be generalized after these 2 cases. Now for case number 2 is free at one end and clamp at the other end. That's the general one, but in most cases, if it is upright column, then one end will be at the top and the other end at the base. So in that situation, we'll call it free at the top and clamp at the base. So if it is lying horizontal, then both are top, both are base, then one end is free, one end is clamp. So that terminology depends on the orientation of that beam or column. Now what we want to achieve today is to establish 4 things there. One is to look at the behavior of the column, how it deforms. This one we have seen it in the first lecture for column from the simulation work. I will show it again later on when we look at the behavior. And number 2 is to identify the governing equation, which is some authors call it the Euler equation for column, and solve this particular equation. It is a closed form analytical equation which we can solve it. Number 3 is to identify the boundary conditions in order to solve that equation. And number 4 is to determine the critical load, and we want to establish that the expression for the critical load is equal to pi squared EI over 4L squared. E is Young's modulus of the material that made up the column. I is the second moment of area of the cross section. L is the length of that column. So these are the 4 objectives for aim, basically what we want to achieve in this particular part of the lecture. So that's what we want to achieve. Okay, so in the analysis, we look at a column, the length L, and it is clamped at the base. So I just want to see whether I can get okay, it's clamped at the base, and we take the direction upwards as x direction because our bending equation is m equal to d2v dx squared, so it has a derivative with x. P is the force applied at the top acting downwards, so that means it is a compressive force. As we mentioned in the last lecture, if the force is not compressive or it is tensile, then the beam or the structure won't be called column, okay, and it won't buckle under tensile forces. It will only buckle under compressive force. Number 3 is a deflection at any position is given by V. So this is deflection. V is the general deflection at any position X. Now at the top end, or at the free end, the deflection is delta. So delta is a specific value of the deflection on that. So delta V is general deflection at position X, and delta will be the value of the deflection at X equal L. That's what it means. So they are both deflection, but one is specific at one location, whereas V is general. And E is the Young's modulus. I is the second moment of area in the direction of bending. Okay, these are the term used in the analysis. Now let's look at the deformed shape of the column. Figure 1, call it figure 1. Figure 1 shows the initial condition either before P is applied or when P is less than critical. So the column is still upright and P is applied. The height of the column, which is the length of the column, is L, and it is clamped at the bottom, shown by the symbol of clamp there, and it has a reaction R. So if the bottom is A, clamp at A, and free at B, then reaction at A will be RA. Okay, and as P increases, then you can see that on figure B, the beam will start to deflect. It can deflect to the left, it can deflect to the right. But in this particular diagram, we choose to deflect to the left. P is still applied in the vertical direction downwards. Now it follows the beam. As the beam deflect or the column deflect to the left, P is still intact with the beam or with the column, so it doesn't leave the column. So that means as the deflection increases, the bending moment or the moment of P about the origin or the base, or when at X equal to 0, will increase. Now delta is specified is the specific deflection at the top, and at location X, the deflection is V. Okay, so this is the behavior of the beam. Now just note at the bottom there, at the clamp part, there is no rotation of the beam at A, basically the clamp part. Okay, so since there is no rotation, the slope is 0. In other words, the angle between the undeflected column with the tangent to the deflected column at A is 0. The angle is 0. There is no rotation, and since there is no rotation, the value of bending moment is not 0. And at the top, the plane section is rotating, so there is nothing to restrict rotation, so there is no internal bending moment. So that's already explaining the boundary condition of this particular beam. So that's the behavior. It can deflect to the left or deflect to the right. Now let's look at how we analyze this particular beam. Okay. Now, again, this is a repeat of the diagram, figure 2. A, B is the same as we've seen before. Now, figure 2, the third figure on the right, on the most part, we are cutting the beam at location X. So we cut the beam at location X and show the internal moments. We don't show the internal forces for this one, it's too crowded. So the internal moment is given by M on two parts of the cut. One of the on the top part of the bottom, the top cut of the bottom part, and the other one is on the bottom cut of the top part. So hopefully you can follow the language there. Okay, so the direction is clockwise on the top part and anti-clockwise on the bottom part. So we only take equilibrium either the lower part of the column of the cut or the upper part. So the rest of the forces are still intact. I think there is one more force, P, at the cut, at the place where it is being cut there to maintain equilibrium. So I put that in for completion of the diagram. It doesn't affect the moment equilibrium because P is located at 0 distance from the place of the cut, internal. So I just put there still P. Okay, so now this is additional to the notes. Make sure you put in your downloaded there. Now look at the displacement at the top, at the free end. The total displacement at the free end is delta. Okay, this is delta. Now the distance between P at the top with the place where we cut, this distance is delta minus V, because the total length is delta, and at the place of the cut there's a displacement V. So the distance between P and the location where we cut is delta minus V, and this is an important quantity when we comes to equilibrium. Okay, so anybody not clear on this particular part of the notes? Okay, right, so what we want to achieve or establish is every part of that column, whether it is in the undeformed or it is in the deformed state, equilibrium is maintained. So at every section. Now for equilibrium to be achieved, the conditions are the summation of F is equal to 0 and the summation of moment M equal to 0. Now if you look at summation of F equal to 0, then RA equal to P. Okay, so the reaction at the base is equal to the force acting at the top. Now deflection, this is the general relationship between bending moment, shear force, deflection, and slope. For bending, we have seen this one before. EI d for V dx to the 4 is minus W. W is uniform distributed load. EI d3V dx cube equal to V. Okay. And EI d2V dx square equal to M. The slope dV dx equal to theta. So these are the 4 equations. that we have seen in our previous lectures on bending moment. We call it bending moment relation. E and I is defined as the Young's modulus and second moment of area. So we will use this for the case of this bending moment. Now we take a cut, okay, a cut there, and the moment equilibrium summation of m equal to 0, and we take the equilibrium at the cut and above the cut. Okay, at the cut and above the cut, because we do not want RA to come into the equation, making it simpler. And when we do that, the equilibrium is taken at the cut, so you can put your fingers at the cut and see where the P give which moment, direction of moment. So at the place where we cut, the bending moment is m, and due to P, it is at the distance delta minus V. So we have P multiplied by delta minus V equal to 0, and the direction of P multiplied by delta minus V is opposite to this M, so it's negative. Okay, so this negative P is because the direction of moment due to P is opposite to the direction of internal moment M at the place where we cut for this particular part of the beam. So we rearrange this, we get M equal to P delta minus V, okay, P delta minus PV. Okay, now we rearrange this to get M equal to EI d2V dx square, and this is equal to P delta minus PV, and we get EI d2V dx square plus P multiplied by V equal to P delta. And we divide all term by EI, we get d2V dx square plus P over EI multiplied by V equal to P over EI delta. So this is the equation that we need to solve. It's a differential equation of order 2 that we need to solve to get the expressions for V. Okay. Now, as I said, this is as we follow from the previous one, P over EI we put in as equal to K square, where K we define K equal to square root of P over EI. Now, if we put that K square into the equation, then the Euler equation become d2V dx square plus K squared V equal to K squared delta. So this is a differential equation, not partial differential equation, it's complete differential equation of order 2. So the solution to this is 2. One is complementary function and the other one is particular integral. So the solution, the proof of this you have to check with the mathematics books. So the solution is V equal C1 sine kx plus C2 kx as the complementary function and delta as the particular integral. Okay, so the full equation becomes C1 sine kx plus C2 cos kx plus delta. Okay, that's the full equation. And C1 and C2 are constant. that we have to determine from applying the boundary condition of the column. Okay. And boundary conditions are known values of the columns. Now, what are the known values? Usually deflection values, if we know exactly where they are. For example, at the constraint it is 0, then that place will become a boundary condition. If it is free end, then bending moment is 0. So m equal to 0 is also a boundary condition. If there is no rotation, the slope is 0, then dv dx equal to 0 at that location, then that location will become the boundary condition. So usually at the support or at the place where there is no support is the boundary condition. So known values of v at a particular location is a boundary condition. It's called a boundary condition. It is the known values at that boundary. For bending of this nature, then m equal to 0 at known is also a boundary condition. So not just for column, but other bending analysis. For example, if it is connected by pin and it can rotate, so at the pin support, bending moment is 0. Okay, proceed on from here. C1, C2 constant from obtained from boundary conditions. Now, since we know that one of the boundary condition at the base there is no rotation, so dv dx is 0. So we need that differential equation, the differentiation of that. So dv dx, we differentiate equation 11, so we get k c1 cos kx minus k c2 sin kx. Delta, when we differentiate with x, equal to 0, so it doesn't appear in dv dx. And we also need the next differentiation. So we differentiate dv dx again, we get d2v dx square. Why we need this? Because m equal to ei d2v dx square. So we differentiate this again, we get d2v dx square equal to minus k squared c1 cos c1 sin kx minus k squared c2 cos kx. Okay, so that's equation 13 on my slide for this one. Yeah, you can just count how many there are of the equation. So the boundary conditions. So at the support, v equal to 0, where it is supported at x equal to 0. Okay, at x equal to 0, v equal to 0. Now this boundary condition come from, and it is because of support. It is not the type of support we are talking about, it is the support. It is supported at that point, then v is 0. There's no deflection at the support. Now, the second boundary condition is at x equal to L, v equal to delta. Okay, this is the free end. And delta is the quantity we put in to identify that location. So it is free end. I don't put there as why is it like that, but it's free end. Boundary condition number 3 or C is dv dx equal to 0 at x equal to 0. Now the reason for this, because it is a clamp support. Now distinguish between A, v equal to 0 at x equal to 0, it is support. And dv dx equal to 0 at x equal to 0, it is clamp support. So it is the type of support that gives this boundary condition. So not just a general support, but it is a specific type of support. So A and C is almost similar, but they are quite different because simply support will also give V equal to 0 at the support, but not dvdx equal to 0, as we have seen in the previous one. So when you write down the reason behind this boundary condition, you have to state that dvdx equal to 0 at x equal to 0 because it is clamped. Okay. So we apply this boundary condition into equation 11. So boundary condition 1 is V equal to 0 at x equal to 0. So this is V. The boundary condition is for V. So the appropriate equation is equation 11 because V equal to C1 sine kx plus C2 cos kx plus delta. So when we put x equal to 0, V equal to 0. So the left hand side give you 0. Okay. And then when x equal to 0, we have sine kx, sine 0, cos kx is cos 0 plus delta. Now sine 0 is of course 0, cos 0 is 1. So we have C2 plus delta equal to 0. This gives us C2 equal to minus delta. Okay, so there's one constant is solved now. So it remains the other one constant, which is C1. Now C1, we obtain C1 by looking at the rotation at x equal to 0, which is dvdx. Okay, so dvdx equal k1 k times C1 cos kx plus k times C2 sine kx. Okay, so this is the derivative of delta. Now the boundary condition, we have, this is the boundary condition, dv dx equal to 0 at x equal to 0 at the clamp side. So we have 0 dv dx equal to kc1 cos 0 minus kc2 sine 0. So sine 0 will give you 0, cos 0 will give you 1. So we have kc1 equal to 0. So k cannot be 0. So the only plausible solution for kc1 equal to 0 is c1 equal to 0. So we get c1 equal to 0. Okay. So we have the values now for C1 and C2. We put back into the equation for V. So we have the equation for clamp-free column is V equal to minus delta, which is C2 cos kx plus delta. The second delta is particular integral. Okay, so this is the solution, but where does P critical come from? Okay. Now we get this particular solution, delta equal to V equal to minus delta cos kx plus delta, and we apply the second boundary condition, which is V equal to delta at x equal to L into this equation. So if we put x equal to L, we have cos kl and minus cos kl plus delta will give us delta at x equal to L. So we get this particular equation, delta multiplied by cos kl equal to 0. Now remember last time on the pin support, we have sine KL equal to 0. So in this today for the clamp free support, we have delta cos KL equal to 0. Now delta is not 0, and the only solution that we have is cos KL equal to 0 because delta is not. So cos KL is equal to 0, and cosine of an angle is equal to 0 when that angle is 90 degrees, 270 degrees, and so on. Is multiple of pi over 2. So to get cos KL equal to 0. So it requires the value of KL equal to n pi over 2, where n can go from 1, 2, 3, 4, and 5. 1, 2, 3, and so on. Now the lowest value of n will give you the first critical load, or the lowest value of critical load. And therefore, the solution KL equal to n pi over 2 will give you the critical load when n equal to 1. So we square this equation 20. So KL, when we square it, we get K squared L squared. On the right hand side, n pi over 2, we square it up, we get n squared pi squared over 4. And K squared is P over EI. This is K squared. And K squared equal to n squared pi squared over 4L squared. Okay, so this is the general equation involving P, EI, and the column dimension. Now, P then is equal to n squared pi squared EI over 4L squared, and n will have the value of 1, 3, 5, and so on. It's multiple, it's odd numbers, odd integer. Now the critical load occurs when n equal to 1, and if we put n equal to 1, we get P critical equal to pi squared EI over 4L squared. So we have established this particular relationship as first, well, at least the aim of this particular lecture. So any questions on this? On the development of this particular equation? No? Any response?
Sir,
No?
why we used n equal 1?
Why we use?
N equal 1.
Okay, not quite clear. Speak up. Why do we use?
Why we used n equal 1?
L, N.
N.
N equal 1.
Yeah.
Because that's the lowest, to get the lowest value of critical load. And it relates to the response. It starts to buckle when n equal to 1. With the shape that we showed you there is a bending, just curve at one type, and at higher n it will start to bend like a wave. So that's higher load. And in a design of column, we do not want it to buckle at all. Okay, so if we put n equal to 3, then the value of P will be higher compared to n equal to 1. So that means it will fail at the value when n equal to 1 first before it actually get to n equal to 3. Okay, so we do not want, in a fail-safe design philosophy, we do not want it to buckle at all. So that's why you put n equal to 1, the lowest value of P, to make it buckle. Okay, so that's the Any more? Okay, let's look at an example. The example that we used before. It is a clamp-free column. Well, that's the shape of that. The thickness is D, which is 24 millimeters. The breadth is B, 120 millimeters, and the length is 4 meters. The same one that we used in the example for pin type, but this time we put in clamp at one side and free on the other side. The Young's modulus is 200 gigapascal. Okay. Well, these are the dimension of the column, and what we are asked to calculate the critical load of the column. Now, I put there critical load to cause buckling, but I don't have to say to cause buckling. Under this buckling analysis, we say critical load, it means buckling. So, but we do not want to have any ambiguities. I put there critical load to cause buckling. Number 2 is the stress, compressive stress due to critical load, sigma critical. These are the two main criteria for fail-safe design. One, it should not buckle at all, and number 2, it should not yield under compression. So P critical to take care of not buckling, and sigma critical to take care of not yielding. So those two that need to be done. I values is BD cube over 12 in the direction when it's going to buckle, and it's usually the lower value. We have already checked this one before. The higher value is DB cube over 12. So it is the lower value of I. Okay, so I is 1.3824 times 10 to the power of minus 7 meter to the 4, which is 120 multiplied by 25 cube over 12. So it is in this Z. I call it IZZ because Y is in the direction of deflection, X is upwards. Okay. Now, this is how it buckle. Okay. You still remember the simulation? So it will buckle along the thinner section. Okay, this is the thinner section. So that means it will buckle in the Y direction, not in the Z direction, according to this figure. Okay, so that's why I is BD cube over 12. If it bend in Z direction, then I will be DB cube over 12. Okay, so that's where that behavior. So critical load is pi squared EI over 4L square. And we put in the values pi square. E is 200 gigapascal, 200 times 10 to the power of 9. I is 1.3824 times 10 to the power of minus 7. 4, there's a 4 underneath that equation. And the other one, 4 squared, is value of L square. And when we evaluate this, we get the value in Newton. And that value is, can you check your calculator? I think I got it wrong there. Can you verify that? 4263.7 Newton. Can you check whether it's right or not?
Yeah, got it as well.
Yeah, which calculator do you use?
FX570MS Casio.
Oh, okay. Same model as mine. Is it calibrated? Is your calculator?
Yeah, it's digital.
Yeah, digital doesn't mean calibrated. Okay, 4263.7 is correct. Yeah, is it correct according to your calculator?
Yeah, it's
Yeah.
correct. Same thing.
Yeah, okay. So that means I've corrected it before then. Yeah, I know one of these lectures, it is calculated wrongly. Okay, so we get P critical is 4.2637 kilonewton. Now the stress due to critical load is stress equal to load over area. Now the load is critical load, so 4263.7, and the area is 0.12 meter times 0.024 meter. So then we get 1.48 times 10 to the power of 6 Newton per meter square. Now make sure when you calculate something in your test, assignment, exam, make sure that number has the appropriate units. The only quantity that hasn't got units in this EM 3172043 stress analysis and design is the unit of strain, which is extension in millimeter divided by length in millimeter. That has got no units. All other quantities have units, so make sure you put in the units. And in the test and exam, normally the examiner or the question paper states which unit you should put the values in as your answer. So for stress, if this is, you have to give the value of the stress in megapascal or meganewton per meter square. Make sure your figure that you put in meganewton per meter square. Okay, so in this case, it doesn't say which unit. So I got 1.48 times 10 to the power of 6, which is, if it were to be in megapascal or required to be in megapascal, then it is become equal to 1.48 megapascal. Okay, so make sure you put the unit right. Okay, any questions on this? So usually the load that we put in, or the column carries, should be less than P critical, and the stress due to that load should be less than yield stress. So that's the fail-safe design. Okay, so that's the end of the clamp-free case for the column analysis. Okay, so basically we have completed the closed form analysis or solution for the column problem. Now the next step is actually to extend or generalize this particular analysis to the other two conditions, which is clamp, so clamp at both ends, and the other one is clamp and pin support. So that one I won't go into the into the analytical detail, but it will be extended to that. So before I go there, I go to the extension. We want to look at equivalent or effective length, because to generalize the solution for the column problem, it's best to introduce intermediate topic, which is effective length. So the lecture notes for the effective length, I also have uploaded in CN. So make sure you download those while I change the slide from this one to to the other one. Okay, on the I will share the presentation notes for the effective length while you download those notes. Okay, so this is the effective length. Okay, effective length of strut. So make sure you download those. So can you see the shared slide?
Yes, sir. We see it.
Yeah. Okay. Have you download those? Yeah. So we look at effective length of strut or column. LE. Okay. The most books will use LE. Okay. Now it's a simple objective, but it is an important intermediate step before we generalize the column solutions. So the objective one is to define the meaning of effective length for column or struts, and number two, to determine the effective length LE of the strut. Okay, those are the two, and hopefully from these two we should be able to generalize the column problem using effective length approach. Okay, so what is the definition? Oh, I lost the definition now. Is it? Yeah, this is the definition.
Sir,
Yeah,
you didn't upload this file.
can hear you.
You didn't upload this one.
Approach.
You didn't upload this one.
Oh, I didn't upload.
Yeah.
Okay, let's check. What did I upload? Oh, it says generalized. I upload clamp free and exercise and generalize. Okay, I'll upload now. Where is? So I upload now. Make sure you have it in front of you. Okay, save this one first. Without the highlighting, right? Hang on. Yeah, it's just one moment. Okay, I'll upload now. Okay, got it? Not yet. Take a while. Right, I saw it on the CN webpage. Got it?
Yeah, just got it.
Yeah. Right. Or maybe the one that I uploaded is actually effective length, but the file name is different. Okay, right. The definition of effective length, LE, is referred to as the distance between zero bending moment points in the column. Okay, that's the definition. Now, I want to spend a little bit of time on this, on the four simulation work that we, four simulation slide that we used previously, just to define what is meant by zero bending moment on those four. So from there, then we get the effective length. So I'll go to pin simulation work or simulation slide. So this is pin. Okay, I'll share. Right, so this is pin. We have seen this one before, right? Now we look at it differently. So this is how it buckle. Just to see, right. So we have seen how it buckle. I just stop at that point, right? So this is how it buckle. Maximum deflection in the middle, and there is zero Y deflection in this one. So X is from bottom up. Now, where is the point of zero bending moment? That's what we are looking for in this whole length of this length of the column. So from X equal to 0 until X equal to L, where on this particular column the bending moment is 0. Now, I don't have the result for bending moment on this particular simulation, but at 0 bending moment, we expect 0 bending stress. And bending stress is sigma x on this simulation software that I'm using. So now I will plot or show the fringes for X stress on this beam. Can you see that? Red represent the highest stress. The blue represent the lowest stress. So red is positive, blue is negative. And you see the scale there, the green is 0. Can you see that? Now, where is the green part? Is the point there. The tip there is green. And the other one is this one, this point is green. Now, as it moves in that direction there, the place where it is pin is actually 0 bending moment. 0 stress and 0 bending moment. So on this particular column, the distance between the end of the beam, end of the column, is the effective length according to the definition. Okay, so effective length LE for pin support will be the distance between pin to pin on this beam, which is the length of the column. So that's the first one. Now look at the clamp condition. Okay, so I'll go for the clamp condition. Because we have not seen the clamp, we don't actually analyze closed form to find that one. So we'll rely on this. Okay, right. So this is the clamp condition. Okay, I'll share it now. Okay, now it's visible, right? So this is the clamp condition, how it deform. Okay, there you are. I just look at the most worst case there. Stop there. I should go on just about there, right? Now this is the clamp condition. Actually, we have not solved it, so we want to use effective length approach in the solution for the clamp side. Now the effective length is that it is the location of 2 points on the beam where the bending moment is 0. So on this particular work, we'll find where the bending moment is 0 and where sigma x is 0. So I'll share this fringe, colored fringes there. You see the color there? Now using the same scale of color there, the green is zero bending stress. Now you can see that the end of that is blue and red at one point. The middle is also blue and red. That means one side is compression, one side is tension. Now at this point there, it's about 1/4 from each end. We have a green band of stresses there. Okay. Can you see that? 1/4 from left end and 1/4 along the beam from the right end. So we have a green band of stresses there, which is 0 value according to this X stress color scale there. So that means the distance between these 2 points. Okay, can you see that? Okay, between these 2 points will be, so between these 2 points there. Okay, this point and that point will be the effective length. So if I take 1/4 from there, 1/4 from there, that leaves me effective length there is half of the total length of the beam of the column. So that's the meaning of distance between 0 bending moment according to the definition. Okay, now let's look at the other two conditions. So we have already seen pin, clamp. Now let's look at other condition. Free clamp. Or clamp free condition. So we have already got the value for this one. Now this is interesting. To me, it's interesting. I don't know about you all. Could be stressful. Okay, this is how this particular beam behave. Okay, we just see how to get pre-critical of this, right? Okay, now in the light of effective length, we are looking for location of zero bending moment. And translated on this diagram, on this simulation work, as zero bending stress. Now let's look at the color fringe for this. Right, just click express.
Sir, are you sharing?
Oh yeah, sorry, forgot to share. So I'm talking to myself. Okay, I'll share. Yeah, I thought it's once you click to that, it's automatically shared. Okay, I repeat then. Okay, can you see now?
Yeah.
Yeah. Okay, this is how it behaves. Right, we have seen this one, the first lecture on column, and we have already calculated P critical for this particular case. So now we are looking for effective length. So now this is how it deform. So I just want to have a look at one particular location and then stop. Now this is how it deform. Now you can see that at the bottom there, where it is clamped, okay, the stress is not zero. You have high values on one side, positive, and another high almost equal in values in the negative. So that's characteristics of bending. So on one side is positive, on the other side is negative of almost equal value. So that's characteristics of bending. So that's what happened at the place where we clamp. That means there is internal bending occur. Now let's look at the top where it is free. You can see it is a uniform green color. Okay, at this point. So that means there is no stresses in there according to this color scale, because for green we have a positive 3.5 slightly up and then negative 0.8 slightly down. So on the green actually zero. So now you only have 1 point of zero bending moment on the beam, on the column. Now effective length says that it is the distance between 2 points on the column where the bending moment is zero. Now for this case you only have one. So in that sense, what we got to do is to have an imaginary column on the other side of this beam. Okay, so the distance will be twice the length of the beam. Okay, we'll see that in the lecture notes later on. Now the condition that we have now is actually only 1 point of zero bending moment. So we won't measure 1 point with another the same point. That will give you zero. So we'll look for another point which is imaginary extension of this but equal in behavior. So we'll see how that one will work. Okay, now the last example is the other one. So we have seen 3. So which one is it? Pin and clamp. We have not seen pin and clamp. Right, so this is pin clamp. Just share again. Yeah, it's a bit inconvenient to share every time you change to new slides. Okay, now you see the screen now. Is it visible? Yeah. Okay, how it deform? This is how it deform. Oh, this is clamp at the bottom. Okay, clamp at the bottom. Free pin at the top. Okay, just want to show that. Okay, just stop that. Oh, sorry. Okay. So what is it that we are looking for? Point of zero bending moment or point of zero stress. Now, in order to see that one, I just put the colored fringe X stress on there. Right. Now we are looking for all green areas. Now you can see that all green areas occurs at the pin at the top, and another all green areas is a bit, maybe 1/3 or 1/6 away from the bottom part. Okay, this one there. Can you see the arrow on? Yeah, this one there. Yeah, this area. Okay. Yeah, this is the area of zero bending moment. So in other words, the effective length is basically the distance from the top until this particular distance. Okay, until this distance. Right there. So that's the effective length from the definition. Okay, so there you are. So in other words, it's important to understand the behavior of this beam column under that particular load, and then check back against the definition of effective length. So now I'll continue back to the lecture proper. So just bear in mind the definition and the location. Of effective length. All right. So for example, these are the definition there. Zero bending moment point for strut AB. For case 1, pin support. So it is the distance between the two ends. So LE will become equal to the length of the column. And this is what we see from the simulation just now. So zero bending moment occurs at A and at B. So effective length LE is equal to the length of the beam. Okay. Now case number 2 of pin strut. If you want to calculate, then this one is looking for zero bending moment. So V equal to C1 sine Kx. dVdx is Kc1 cos Kx. And moment is d2V dx square, which is K squared C1 sine Kx. So M equal to 0, bending moment equal to 0 when x equal to L, and bending moment equal to 0 when x equal to 0. So basically the distance between A and B. So this is one if you want to calculate from the solution of strut. So we still get the same value. If we observe it from simulation work, we get the same value there. So that length of AB or distance of AB, which is the length of the column, is the effective length for the case of pin. Now let's look at for the clamp free, the one that we showed that only one point physically or in real term, only one point with zero bending moment, which is at the top, because the other one is clamp and there is no zero bending moment. Okay, so for this case, you can read the text there, how it is being done. We can see that the effective length is 2 times L. How is that? This is what I said when we said we have an imaginary beam opposite to the imaginary column, opposite to the column that we have. We only have a column from A to B with 1 point of zero bending moment, and effective length requires 2 points on the bending moment on the column. So now we have this AB dash as the imaginary column, which is a mirror image of the actual column AB, so that we can identify the zero bending moment. So effective length for this case is twice the length of the column, 2L. Okay, so that's how it is being determined from the definition. Now from these two that we want to generalize the solution. So for the effective length of clamp free will be 2L. So if L is 4 meters, then effective length is 8 meters. Okay, that's how we get the value. Okay, so that's how it is being done. So what we'll do now is to generalize this particular topic. Okay, any questions on this? No? No question. So either it is not clear or yeah, it's difficult to pinpoint who is here, but since we are not face to face. Okay, any question there? Okay, so we look at generalization from those two and from the effective length definition. So I'll go to the next slide. I'll share this slide. Okay, can you see the slide now? Yeah. It's already shared. Can you check the, can you download? Is it having the same file or
Yes.
same file?
Yes.
Okay. Now generalized column and struts. So as I said, we won't go into the detail as a closed form solution, but we will generalize from those two cases and also the effective length. Now, first to understand the general column behavior, I think we have done that through simulation work. To understand the boundary conditions, also we have already done on at least two types. Now the next one is to establish the generalized critical load expression. Some of you call it equation, some call it formula. Okay, can you correct the spelling there? Critical. Okay, so the spelling on your file, I think it's replace T with L. I only observe it now. Okay, so that the critical load, P critical, is represented by an expression P crit equal to pi squared EI over K, a factor, multiplied by L square. And K multiplied by L is what we call effective length square. So it is easier to remember. Okay, so we will look back at what we have done. So on both types, we have pi squared EI on the numerator. And for the simply support or the pin support, we have pi squared EI over L square. For the clamp free support, we have pi squared EI over 4L square. Now we want to establish this relationship from those two cases. And in this case, P critical equal to pi squared EI over KL in bracket whole thing square, where KL is equal to LE effective length. Okay, so that is simpler for us to show. So for K equal to 1, we have P critical equal to pi squared EI over L square. So this one will give you pin support. So pin support K equal to 1. For the clamp free support, we can put K equal to 2 or LE equal to 2L. Okay, from this general equation. So by doing that, then we have P critical equal to pi squared EI over 4L square. Okay, so at least the L effective, if LE concept applies to these two cases. Now, if we have other two cases, the clamp pin will show you where the effective length is. So we still apply P critical equal to pi squared EI over KL square. And then we apply to the other two cases by looking at effective length. So for pin clamp, we showed you where the points of zero bending moment are. This will give us K equal to 0.7. You can work this one out either experimentally or you can have a closed form solution. I won't go through that one. Or from the simulation work that we developed, we showed you just now, to point out to get the distance between two zero bending moments. So in this case, effective length is between these 2 points, 0.7 L. So if we apply that, then we can put in this equation LE is 0.7 L of the beam and square it. So that's how useful, how to use this effective length concept. Okay, so we can work this one out, the general displacement, K squared equal to PEI. So we have this deformed shape, and L effective is 0.7. So we get P critical equal to pi squared EI over 0.7 L square. Okay. Right, and the last one is clamp. So from the simulation work, the LE is 0.5 L. Okay, so these are the zero bending moment points to define effective length, and we could calculate from the first principle if we wish to find that one, and then at the end we get P critical is equal to pi squared EI over LE square, and LE is 0.5 of the length. Okay, so this is how we generalize the equation now from the effective length concept. Okay, just remember it is the two distance between two zero bending moment. So now we can put everything into summarize this one. So we use the expression P critical equal to pi squared EI over K, which is an effective length factor, multiplied by L, and we tabulate this for 4 types of situation, and I put the beam to save space in horizontal direction, right, to show the difference there. So to get the expression for P critical in this particular form. So the effective length pin is L, clamp free is 2L. Okay. Pin clamp is 0.7L. And then clamp is 0.5L. Okay, put that in the equation, then you get the critical value, critical load value. Okay, so any questions? No? Okay, now we conclude this one. So what we have so far, the skill that you should be able to calculate critical load, buckling load, and apply that into fail-safe design. Calculate the stress at critical load and limit those stress apply for allowable limit. Now the fail-safe design that we are talking about is elastic design. So the allowable limit for the stress is yield stress, not UTS. Okay, it's yield stress. If you use UTS, there will be some plasticity in the in whatever structure that you are applying. So normally for fail-safe, it is elastic design, limit against yield stress, or limit against proof stress if the yield stress is not clearly defined. Okay, and finally, I put that questions for e-learning. So if you want to respond to this, can respond it. I will put a link to this part later on. So this is the thing that you should be able to answer. So the generalized equation for critical loads, boundary condition, and effective length, and so on. You have all this in your exercise that I submit, that I upload. Okay. Right. So I think that's all. I think we completed all the CLOs now. So on Thursday, we will do some revision course, revision topics that you want to revise on. I'm not going to repeat the lecture, but I will go through the at least test one first question on Thursday. Okay, to explain the first one, because the approach that I think we'll need more exercise on those cases. Okay, on Thursday, I'll go through test one first question. Okay, so make sure you come. Okay, or any issues that you are not understand any particular lecture, you can post the questions on Thursday. Okay, so I think that's all for today, and we'll start some revision work on on Thursday, not next week, on Thursday. Right. Okay, any question? Okay, so thank you very much. We still have 1 minute to go. So if you have anything that you need to sort out before I end the meeting in about 30 seconds. Okay, so thank you very much. I'll stop recording.